Welcome to learn Fundamentals of Data Structures and Algorithms course. In the last session, we have discussed the fundamentals in algorithms. We have designed the algorithms for solving simple problems. Clearly, an algorithm is defined as an unambiguous procedure which consists of a finite set of well-defined instructions, each of which requires a finite amount of storage, and each of the instruction requires the finite amount of time to complete the execution, and it can be executed by a mathematical machine. And then we have explored the criteria, characteristics, areas of application of study of an algorithm. We have designed the algorithms for solving some simple problems. In this session, we focus on the performance analysis of an algorithm. Performance analysis of an algorithm, which indicates that we need to analyze the algorithm for two different things. One is space requirement and another one is the time requirement. Performance analysis in the sense that we need to find the space complexity of an algorithm and the time complexity of an algorithm. The performance evaluation is classified into two ways. One is a priori estimates, second one is a posteriori testing. Priori estimates, which means the performance analysis, posteriori testing, which means the performance measurement. Once an algorithm is designed, we need to verify the correctness of an algorithm. After ensuring the correctness of the algorithm, we need to analyze the algorithm for two different things. One is the space requirements and another one is the time requirements. Space complexity, which defines how much amount of computational memory is required to run the algorithm. Time complexity defines how much amount of computational time is required to run the completion of execution of the algorithm. In general, we can evaluate the performance of an algorithm in two different categories. One is a priori estimates, which means the performance analysis of an algorithm. A priori estimates in the sense that once the problem is converted into an algorithm, then we need to find the space requirements and time requirements of an algorithm. That is performance analysis. Once the algorithm is validated, then the performance analysis is over. We can convert the algorithm into a program. After the algorithm is converted into a program, we need to find how much computational space and time is required for the program. That is nothing but performance measurement. So, a posteriori testing, which means once the algorithm is converted into a program, we need to find the corresponding space and time requirements. After the algorithm is converted into a program, we need to have the performance measurement of the program, but before the program, right, we have the algorithm. For the algorithm, we need to measure the time and space requirements. that is to be the performance analysis. In the performance analysis of an algorithm, right, we need to focus on two complexities. One is the space complexity, second one is the time complexity. The space complexity of an algorithm is computed before the algorithm is converted into a program. So, here we need to determine the space requirements of the algorithm. Time complexity of an algorithm defines the time requirements of the algorithm. That means how much computational time is required to complete the execution of an algorithm. Hence, in the performance analysis of an algorithm, we need to focus on two important complexities. One is the space complexity and another one is the time complexity. Now, let us explore the space complexity of an algorithm. Space complexity of an algorithm defines the space or memory requirements of an algorithm. In general, the space complexity of an algorithm consists of two important components. One is a fixed part component, second one is a variable part component. What is a fixed part component? A fixed part component which represents the memory which is independent of problem instance characteristics. Independent of a problem instance characteristics. For example, number of inputs, size of inputs, the size of outputs. These are the problem instance characteristics. Fixed part component involves a memory for the problem instance character independent of the problem instance characteristics. It includes the memory for the actual code, simple variables, constants, fixed size variables, fixed size component variables. In general, the algorithm's space complexity is computed by adding the corresponding fixed part component memory plus variable part component memory. In the fixed part component, the memory is completely independent of the problem instance characteristics. That means the memory is completely independent of the number of inputs, size of inputs, outputs. So, what is actually included in the fixed part component means the fixed part memory includes the memory associated for the corresponding code. A simple variables memory is included in the fixed part. Constants memory is included in the fixed part. Fixed size component variables memory is also included in the fixed part memory. In general, fixed part memory is completely independent of the problem instance characteristics. Second one is the variable part memory. Variable part memory, this is completely depend on the problem instance characteristics. This is completely depend on the problem instance characteristics. Here the component variables, whose size depends on the problem instance characteristics. For example, it includes the space for referenced variables, space for recursion stack space is also included in this variable part memory. In general, assume a P is an algorithm. S of P defines the space requirement of an algorithm. The space requirement of an algorithm, S of P, this is equal to a fixed part memory plus variable part memory. S of P is equal to a fixed part memory. A fixed part memory is a constant, so let it be C, plus variable part memory is S a P of instance characteristics. Since the fixed part memory is completely independent of the problem instance characteristics, let C represents the fixed part memory and SP of instance characteristics. This defines the variable part memory. Combining the memory for both fixed and variable parts, we have the space requirement of an algorithm, which is defined as S of P is equal to C plus SP of instance characteristics. For example, let us find the space requirement of this algorithm. Quadratic determinant. Assume the parameters are, for example, A, B, C. Let us return the determinant of the quadratic equation. Return B square minus 4AC. Assuming the algorithm name is a quadratic determinant, A, B, C, these are the formal parameters. A, B, C are formal parameters. The algorithm likes to return this expression. For example, D is equal to B square minus 4AC. In this example, we have only the fixed number of inputs. The inputs are given in the variables. For example, formal parameters A, B, C. formal parameters receive the corresponding input arguments. Fixed number of inputs, so fixed size components, 3 variables are there, a, b, c. During the execution of the algorithm, whatever the values of the variables a, b, c, integers or floating point numbers, right? Here let us assume that each variable is taking one word of memory, So clearly the variable a takes one word of memory, and the variable b takes one word of memory, and the variable c takes one word of memory, whatever the values of a, b, c, right? So clearly in this algorithm we have the fixed size component inputs. 3 inputs are required, a, b, c. Assuming that 3 variables, each of these 3 variables requires one word of memory, clearly the total memory required to run the execution of this algorithm is at least 3 words, 3 words plus the actual space required to hold the complete algorithm. So in this case the problem instances are completely independent of the problem instance characteristics. So in this case we have only the fixed number of inputs. Fixed number of inputs require 3 words of memory. There is no variable part memory. Variable part memory is completely 0. So the space requirement of this algorithm is S, quadratic determinant is at least 3 words of memory, greater than or equal to 3 words of memory, since the algorithm, right, requires some x words of memory. So x plus 3 words, or at least 3 words of memory is required to complete the execution of this algorithm. Now consider the second example. Let us consider the algorithm to find the sum of the n elements which are stored in an array. Algorithm sum A array comma n. What is A array? A is one dimensional array which consists of n inputs, a1, a2, a3, etc. an. N represents the size of input. N represents the size of input. Let us design the algorithm S is equal to 0 for I is equal to 1 to n do S is equal to S plus A of I for n's here, and for assume that the sum variable S is returned to the calling place, return S. This is end of some algorithm. Assuming that a small a is a one dimensional array which consists of n inputs, a1, a2, a3, etc. an. That means n represents the size of input array. We need to find the value of S is equal to a1 plus a2 plus a3 plus etc. plus an. To evaluate the right hand side of this equation, we have applied the iteration using one some variable, for example S is equal to 0. Using the for loop for I is equal to 1 to n do we have returned the code s is equal to s plus a of I, for ends here n for, then the sum is stored in a variable s here, and finally the value of a variable s is returned to the calling place. In this algorithm we have to analyze, right, the fixed part memory as well as the variable part memory. Now let us find, right, what are coming under the fixed part memory. Fixed part memory includes the memory for simple variables, constants, fixed size, component variables, corresponding memory for the code itself. Now in this algorithm we have introduced the variables s. S is one variable and I is one variable and n is one variable. During the runtime one can input, right, 5 numbers, n is equal to 5. Another one can input, right, n is equal to 25 numbers, or I can input, right, n is equal to 10 numbers. So whatever the values of n, what is n? N represents the size of input. Whatever is the size of input, clearly the algorithm takes the memory for the variables s, I and n. Let us assuming that the variables s requires 1 word of memory, n requires 1 word of memory, and I requires 1 word of memory. So clearly these are fixed size component variables. These 3 variables require 3 words of memory. So at least 3 words of memory is required in the fixed part. Now analyzing the variable part, in variable part n represents the size of input. Suppose n is equal to 2, memory is required to hold the array elements, say a1 and a2. When n is equal to 5, memory is required to hold the array elements a1, a2, a3, a4, a5. When n is equal to 100, memory is required to hold the 100 elements in the array a1, a2, a3, etc., a100. Compared to the previous algorithm in the quadratic determinant, during the runtime we have only the fixed size component inputs. Only 3 variables are required, say formal parameters a, b, c. So there, right, and the fixed part memory requires exactly, right, for example 3 words of memory corresponding to the formal parameters a, b, c. Here in this example, during the runtime, when the number of inputs, size of inputs is 2, memory is required to hold a1 and a2. So it requires only 2 words of memory. When the input size is n is equal to 5, during the runtime, memory should be allocated for the variables a1, a2, a3, a4, a5, assuming that each array element requires 1 word of memory. So in total 5 words of memory is required. When n is equal to 100, it seems that 100 words of memory is required. So in general, if the input size is small n, n represents the input size. Since here the problem instances are characterized by the size of the input, the variable part memory is depend on the problem instance characteristics. Based on the size of input n, it requires n words of memory. Understand? fixed part memory we have 3 votes, and in the variable part memory we have at least n votes of memory. So, combining these fixed part and variable part, we have S of p is equal to C plus Sp of instance characteristics. Fixed part memory is, for example, 3 votes, and variable part memory is, for example, n votes, 3 plus n. Since the program or algorithm itself takes some x votes of memory, so combining with 3 plus n, S of p, that means S sum of n, S which indicates the space requirement of an algorithm sum, with n represents the size of the input problem instance characteristics. This is greater than or equal to n plus 3 votes. So, this is an example which includes the memory for fixed size variables as well as a variable part memory. Both fixed part memory and variable part memory are required to run the completion of execution of this algorithm. Consider this example. Next example, let us try to convert the array sum into the recursive procedure, recursive algorithm. Example 3. A recursive sum of array elements. Given there are n elements in the array a1, a2, a3, etc. an, we need to devise a recursive logic to find its sum. For example, algorithm recursive sum A array comma n. What is A array? A array is a one-dimensional array which consists of the array elements a1, a2, a3, etc. an. What is n? N represents the size of input. We need to find S is equal to a1 plus a2 plus a3 plus etc. an. The sum of the array elements should be obtained and the result should be returned. Now, in the simplest level, we can check if n is equal to 0. If n is equal to 0, then return 0, else return a recursive sum of A array comma n minus 1 plus A of n. A recursive sum, this is the name of the algorithm. Initially, the formal parameters are array A with n elements. Here, the same procedure or algorithm, recursive sum is invoked. Recursive sum with the parameters are changed. A array comma n minus 1 plus an, the element nth element is separated, and this is added with the remaining n minus 1 elements in the array. So, logically, if S is equal to a1 plus a2 plus a3 plus etc. an, when this is defined as sum of A array comma n, then a1 to a n minus 1 can be defined as sum of A array comma n minus 1. So, in general, recursive sum of A array comma n, this is equal to recursive sum of A array comma n minus 1 plus A of n. So, in this case, the if write ends here, say end if, then opening curly brace closes here, this is the end of a recursive sum algorithm. In this case, we need to find out the space requirement of this algorithm. That means, what about the recursive state space, right? Since the recursion is introduced here, algorithm name, same algorithm name is introduced here. Let us try to find out the recursion stack space. Recursion stack space required to run the algorithm recursive sum A array comma n. In general, the recursion stack space, which includes the space for formal parameters, local variables, and return address. In each recursion, space should be associated, or space is required to hold the corresponding formal parameters of the algorithm call. Then it includes the memory for the local variables, and it includes the memory for the corresponding return address. For example, initial call is recursive sum A array comma n. This invokes the recursion recursive sum of A array comma n minus 1. Then this invokes the recursion recursive sum of A array comma n minus 2, etc. Last but one, recursive sum of A array comma 1. Then the last recursive call is recursive sum of A array comma 0. Clearly, we have defined the termination condition. When the parameter, right, n becomes 0, that means here in the function call, if the actual parameter, right, n becomes 0, then a recursion is terminated, since the procedure, right, or function returns a value 0. If n is equal to 0, the value to be returned is 0. So finally here the actual parameter n is 0, simply this returns a value 0. Then recursive sum of A array comma 1, this is invoked, right, in the previous call, recursive sum of A array comma 2. Likewise here the value is returned to, right, the previous call, this is returned to the caller, here this is returned to here the caller, and this value is returned to the caller here. The initial call is recursive sum A array comma n, which invokes, right, this recursion, then this invokes the next recursion, this invokes the next recursion, etc. Finally recursive sum of A array comma 1 and recursive sum of A array comma 0. In each of these recursions, what happens, the space should be associated for the formal parameters, local variables, and the corresponding return address. So in our case, in each call of the recursion, in each call of the recursion, the memory should be allocated for the value of n, which requires 1 word of memory, and the pointer to the array A which requires one word of memory, the corresponding return address which requires the one word of memory, because the recursive stack space which includes the memory for formal parameters, local variables, return address, right. So, formal parameter here n, then return address, right, one word of memory, and the local variables here in each recursive call we need to find out the corresponding array element memory that is included here, the pointer to the array A. So, in each recursive call we need, right, at least 3 words of memory, 3 words of memory is required in each recursive call. We need to find out the depth of the recursion, because we like to find the total recursion stack space required to execute this algorithm. In each recursive call at least 3 words of memory is required. We need to find out the depth of the recursion. For example, when n is equal to 5, a recursive sum of A array comma 5, this is the initial call. This invokes a recursive sum of A array comma 4. This invokes the recursive sum of A array comma 3. This invokes the new recursive call, recursive sum A array comma 2. Then this invokes the recursive sum A array comma 1. This invokes the next recursion, recursive sum of A array comma 0. Since n is equal to 5, recursive sum A array comma 5, this is simply the initial call. These are the recursive calls. Whichever is the initial call or any of these recursive calls, we need at least 3 words of memory. So, how many times the recursive sum algorithm is executed? 1, 1, 2, 3, 4, 5, 6. 6 times the recursive procedure is 6 times the recursive procedure is executed for n is equal to 5. In general, if the input size is n, initial call is recursive sum of A array comma n. This is followed by how many recursive calls? Here one initial call followed by 1, 2, 3, 4, 5, 5 recursive calls, n is equal to 5. So, in general, when the input size is n, one initial call calls n recursive calls, n recursive calls. So, a total number of calls is n plus 1 calls. So, clearly the depth of the recursion is n plus 1. In each of these n plus 1 calls, we need to have at least 3 words of memory in each recursive call. Recursion stack space requires 3 words of memory. Hence, the total recursion stack space is at least 3 into n plus 1 words. Understand? The total recursion stack space required to find the sum of n elements which are stored in an array using the recursive procedure is at least 3 into n plus 1 words, that is greater than or equal to 3 into n plus 1 words. Hence, in the recursion stack space, we need to include the space requirement for the formal parameters and the local variables and the corresponding return address. Including all these things, right, in the recursive sum of n elements algorithm, finally, right, we have concluded the total recursion stack space required is greater than or equal to 3 into n plus 1 words. This is the way of finding the space requirement of an algorithm. Hereafter, we will not focus on the space requirement of an algorithm, because the space requirement of an algorithm depends upon the language which is going to be implemented for the algorithm, right. The languages, right, for example C, C++, Java, right, takes a different data requirements, memory requirements. So, the space complexity of an algorithm depends upon the language to be implemented. So, hereafter we will focus on only the time requirement of an algorithm.